So the first couple of slides that I run through, I really don't need you to write anything down. I'll tell you when I want you to start putting things into your notebook or things I think would be good to put into your notebook. In the very first couple of slides, we're just going to kind of see, like, what do the graphs of sine and cosine look like on a coordinate plane? Okay, and so I'll talk about a couple of different ways that we can create those graphs. After we do that, we'll look at some characteristics of the graph. We'll write those things down, and that's basically what your homework is today, picking out characteristics of the graph, but you're not actually graphing. So graphing happens tomorrow. Okay, so we're going to start with graphs of sine and cosine, and I'm going to start with the unit circle. Again, you don't have to write any of this stuff down. It says, use the unit circle to create a table of values for f of x equals sine of x or f of x equals cosine of x. So there are really two functions that we're talking about, and we want to explore them just like we've always explored functions, by looking at what we would maybe call their parent graphs, like y equals x squared or y equals the cube root of x. So I want to look at this f of x equals sine x, and maybe I'll write it as y equals sine x. And I could create an xy table from the unit circle, where x is what I'm putting into sine, so it represents angles, because you take sines of angles, and then y represents what I get out for the sine. Thinking about the unit circle, if I want to find a sine of an angle on the unit circle, I look at what? The sine of an angle on the unit circle is equal to y. Okay, so I'm looking at these sine values that are my y's. Okay. And then I'm looking at my angles, and I'm actually going to be looking at radians. Okay. Okay, now I'm not going to use every angle when I create this table of values. So I'm going to start at 0 radians. If I were to do the sine of 0 radians, the y value is 0. So the ordered pair 0, 0 should be on the graph of the sine function. You're going to see that in a little bit. Okay. I'm going to skip, I'm going to count by fourths. So I'm going to do pi over 4. That's an angle. If I were to do the sine of pi over 4, I'd be looking at the unit circle at its y value, which is square root 2 over 2. Okay. Now, square root 2 over 2 is approximately, as a decimal, just so we're kind of aware, like 0.707. Okay, so a little bit less than 1. Okay. And if I keep kind of rotating around in fourths, my next one would be pi over 2, which my y value is 1. 3 pi over 2, or sorry, 3 pi over 4. That's what I want to do next. In the second quadrant, has a square root of 2 over 2 again, so it's at 0.707. And when I get to pi, I'm at 0. So notice what happened. It went up, because I'm going by fourths. Okay, it went up to 1, and then it came back down to 0. And if I continued that, and I went 5 pi over 4, I'd be at negative square root 2 over 2, or negative 0.7. And then I do 3 pi over 2, which is negative 1. And I could do 7 pi over 4, negative square root 2 over 2. Because I'm running out of room, I'm going to jump to 2 pi, which gets me back to 0. And so I kind of see the same thing. This time I go down to negative 1, and then I come back up, right? And once I get to 2 pi, remember 2 pi is really the same as 0. So if I keep going around, I'm just going to keep getting this same cycle. Kind of like if you remember back to imaginary numbers, cycle divide. Just keep repeating yourself. Okay. So we're going to see that in the graph. And we could do the same thing for cosine of x. And this time I'm just going to go by pi over 2's. So I have less to put up there. But if we were doing cosine of x as our function and putting in different angles, we would then be looking at the x values. So when we put in 0, we'd get out 1. When we put in pi over 2, we'd get out 0, negative 1, 0, 1. And you could imagine like the square root of 2 over 2, negative square root of 2 over 2 are in between those things. Okay. So it does very similar to what sine does, which is it goes up to 1 and then it comes back down, and then it goes to negative 1 and comes back up. But it does it on a different timing on the angle. So instead of starting at 0, 0, it starts at 0, 1.
Does it do the same thing for like degrees, but just a lot slower?
It would do, no, it would do the same thing. The graph in degrees would be the same. It's just that when we graph them, we'll always use the radians. It's just common when you're graphing them to use radians, but you can see it in degrees. Okay. So now I'm going to change it over to a visual so you can actually see what the graphs are going to look like. And we're going to be plotting infinitely many points to make our curve. So what I have up there on the screen, and I know it's hard to see, we've got a unit circle with radius 1. And a point is moving around the outside of the unit circle and has an xy ordered pair everywhere. And what this applet is going to do for us is it's going to graph the functions y equals sine of x. So, well, we know 0, pi over 6, pi over 4, pi over 3, and we would have like gaps in between. This is going to graph all the things in between. Because even though we don't have special right triangles for all angles, we know that in our calculator we can put in other angles. And so, Mason, maybe that's what you're thinking about, doing every single degree, okay? And then doing every half degree and every 10th degree and things like that. Okay, so I want you to imagine, I'm going to click here in a little bit for sine to start. I want you to imagine, like, these are the angles going around, 0, pi over 2, pi, 3 pi over 2, 2 pi. And then I also want you to be thinking about what's happening to y. 0, 1, 0, negative 1, 0, because the y value is your sine. Okay, so you're going to see that get graphed as I select, oh, sorry, red marker. I will use the computer as I select the sine function. Okay, so it's going to start graphing point by point. And so there's pi over 2 and 1, there's pi and 0, there's 3 pi over 2 and negative 1, now we're at 2 pi and 0. And we're just going to kind of repeat. And it's filling in all the little spaces in between. So again, imagine that table of values that I had created. Here's 0, 0. Square root 2 over 2, 1. Square root 2 over 2, 0. Negative square root 2 over 2, because I'd be in the third quadrant here. Negative 1. Okay? And so I'm getting this nice curve. Now, when this continues another revolution, it just goes back to the beginning, but we would understand there are coterminal angles beyond 2 pi, right? So then the wave just continues. And so it's a continuous wave there. Now, if I ask it not to draw the sine function, but I ask it to do cosine, remember what's really going to be the main difference with cosine? Where it starts. Because the cosine of a 0 degree angle, and that little point in the center of the circle is 0, 0. It's going to be different, but we know cosine at 0 is 1. So I'll display the cosine. It's going to start at 0, 1. It's going to come down to 0, and to negative 1, into 0, into 2, and back to 1, at 2 pi. And so it goes. Their graphs are really very similar, right, in look. The main difference would be like where their starting point is, and that's what we're going to focus on tomorrow when we actually graph the sine and the cosine function. Okay. I would describe them as waves. I would describe them as like repeating graphs, so I could just copy and paste, and put that wave right next to itself, and it would be this continuous graph that is sine or cosine. And another word for that might be cyclic, and it just follows a cycle. Okay, so that kind of gives you some reference for what the graphs actually look like and how we could form the actual points from the unit circle, from the ordered pairs. Okay. Now, we're going to draw sine graph and cosine graph just really quickly in our notebooks. So I would, if I were drawing the sine graph, I would probably not draw as much as I have drawn right here. I would draw an x and a y, and I'm going to focus on the positive x from 0 to the right. And then I would plot 5 points. When I ask you to graph tomorrow, I'm going to ask you to label 5 points on your graphs. The first point I would plot for sine would be that 0, 0 point. So we know it starts at 0, 0. The next point I would plot would be at pi over 2 comma 1. And the next point after that will be at pi 0. 3 pi over 2, comma negative 1, and then 2 pi 0. And I would just draw one part of that curve. Now, I will also make note of domain and range really quickly while we're looking at this. One thing I can note about domain is this graph is continuous. It has no start stops. Of course, I have a start and a stop, but I can tell that it's just going to kind of repeat itself over and over again. So I can put anything I want in for x. That would be all real numbers, or in interval notation, negative infinity to positive infinity. And in terms of range, remember range has to do with your y coordinates. So you're thinking about minimums and maximums. What's your lowest point possible for y? -1, and your highest point possible? +1. So you have a range from -1 to 1, inclusive. So you got to use the brackets. That means include -1, include +1, because I can actually be +1 at pi over 2. So this is a shape that you'll get really familiar with in terms of sine. When I was in high school and I learned the sine function, I remembered that it started at 0, 0, and then I remembered mountain high, valley low. You go up first and then you come down. Okay? That was how I remembered sine. Now, we're also going to draw a quick sketch of cosine, but we know there's going to be a change to cosine, right? We're not going to start at 0, 0. We're going to start at 0, 1. Okay, so on my next slide, I have a picture of the cosine graph. Again, I'm not going to draw the whole thing. I'm just going to label 5 points. 0, 1. This is pi over 2, 0. This is pi -1. This is 3 pi over 2 0. Sorry. And this is 2 pi 1. And then I'll connect those. And that's your cosine graph. Now, if you think in terms of domain and range, you're going to say, it's the same thing as sine, right? They're essentially the same graph, just maybe shifts of each other, okay, horizontally. So domain would be all real numbers, and range would be -1 to +1. Yes, sir.
Are we going to talk about tangents?
Yes, on Monday. That is their graphs. The other graphs are all kind of special because they have asymptotes. You think about the unit circle, tangent, cotangent, cosecant, and secant can all be undefined at certain spots. So you have to have an asymptote there. They work a little differently. Only cosine and sine are these nice smooth curves. Okay, any questions about cosine? Okay, here are a couple definitions. We're going to have a little bit of vocab. We'll look at what they mean on the graphs. And then finally, after the vocab, we'll get into what you're actually going to be doing on your homework, which is finding amplitude, period, and starting points. Okay, amplitude is defined as half of the vertical distance between the highest and the lowest point on the graph. So that would be min and max. So again, stressing, if you're looking at a picture of a graph, to identify its amplitude, you don't want the distance from the minimum to the maximum, you want half of that distance. That's its amplitude. And amplitude is a distance, so it's always positive. Okay, you'll see that when I actually like put in how you identify amplitude. We're going to use an absolute value for it. It's always positive. Okay. I'm going to scroll back real quickly to the cosine graph, and we'll just kind of look visually at what amplitude means. Okay. So remember, amplitude is half the distance from the lowest to the highest point. So there's my min and my max. What's that distance from -1 to 1? 2, and so half of that is 1. So the amplitude equals 1. You can also see amplitude as the distance from the midline to the maximum or the midline to the minimum, if you see it a different way, okay, of the graph. Okay. So you might make a little note if you wanted to. Amplitude of parent graphs is 1. The other word that we use for graphs of trig functions, and this will include, amplitude is only for sine and cosine, but period will work for all 6 graphs. A period represents a horizontal distance between a point on the graph and the point where the graph begins to repeat itself. So I also think when I'm thinking about periods in high school, I feel like my math teacher must have said the word cycle a lot. So I always think about like it's one cycle of sine or one cycle of cosine before I could just take that cycle, copy and paste, and get a nice smooth wave. Okay. So I'm going to go back to the other slide with the cosine graph again. We'll look at period. You know, I've drawn it where I did the red so we can find the period really nicely, right? If I start at 0, 1, I'd have to draw all this stuff up to 2 pi 1, and that's when I could like start copy and pasting and just like produce the same curve over and over again. So what's that horizontal distance?
2 pi.
2 pi. Note that you don't have to start from 0 to get a period. You know, someone might have looked at that as like maybe they were looking at this lowest point right here. When's the next time that I get to that point and I start repeating? Right over here, which what's the distance from -pi to pi? Still 2 pi. So regardless of which points you choose on the graph, your period, you know, Dylan chooses a different set of points, he's still going to get the same period as we are, which is 2 pi, because that is continuous throughout the graph. So that's one cycle. And sine would also have a period of 2 pi. So you might write here the period of the parent graphs is 2 pi. Just take a quick moment to think to yourself, why is that? Why is the period one cycle 2 pi? Because that's one revolution of the unit circle, right? And then when you get right back to 2 pi, you just start repeating yourself as you go around the circle. Okay? So one revolution of the unit circle is one period. Okay, now, we're not just going to graph y equals sine x and y equals cosine x. There are going to be other numbers in the graph. So just like when we start off in Algebra 2 graphing like y equals x squared, then we add these parameters like a, h, and k, and they do things to the graph. We do the same thing in trigonometry. We use different letters. Okay, don't know why. They are A, B, C, D. But as you're jotting those down, maybe think about like which one of those letters is related to the A from A, H, and K, which one is related to H, and which one might be related to K. So you have two general equations, y equals A times sine the quantity bx minus c plus d. And then similarly, y equals A times cosine quantity bx minus c plus d. Think about, like, I'm going back to quadratics because we spend a lot of time with quadratics. Think about that quadratic, y equals A times the quantity x minus h squared plus k. The a's in this general form are going to be very similar to the a's we've always worked with. Do you remember what a would do to your graphs? Stretch or shrink, right? Make it skinny, make it wide. Okay, so it's going to be part of stretch or shrink. And for us, that's going to affect amplitude, right? It's going to be a vertical stretch or a vertical shrink. So that would be me taking my wave and pulling it up, making it taller, or pushing it down and making it shorter. Okay. Notice that for amplitude, there's my absolute value of A. That's because amplitude represents a distance. Therefore, it should always be positive. Please don't give me negative amplitudes. What if A is negative, though? What would that do to your graph?
Flip it.
It would flip it, reflected in the x-axis. So that's something also like you can practice tonight on your homework. If you have a negative A value, just make a quick note up to the side. This graph gets reflected. Because that will change our graphs when we graph them tomorrow. Okay, so what letter back with A, H, and K was responsible for horizontal shifting? A, H, K. H, right? X minus H, we move it right or left. And H always looked like the opposite of what it was. If it said like X minus 5 squared, it would go to the right 5 and left. Okay. Now, the one that's most like that is going to be C. But we have this like little complication there with B. So B is actually something you have studied a little bit before. It's kind of like A in stretch and shrink, but it's for horizontal stretches and shrinks. Now imagine what would happen if I took the waves on the previous slides and I stretched or shrunk them horizontally. It'd be like playing with a slinky, right? Be pulling the wave out and stretching it, or I'd be pushing the wave in, so it was like a lot of waves happening. So one thing that B will affect, that's that horizontal stretch or shrink, is going to be a period. If I stretch out my slinky with B, multiplying it by that X, if I stretch that slinky out, I'm changing the period. It's not going to repeat every 2 times, it's going to take longer. Okay. Or if I shrink my horizontal, or shrink my graph horizontally, then my period is going to happen a lot faster.
So the period can be negative?
We really won't have horizontal reflections in the y-axis, so no, you won't have negative periods. I would argue it should be absolute value B then, if you want to. I don't think I ever give you a negative B, but if you want to put an absolute value. Because in the definition it's a distance, it should also always be positive. Okay. Now, H was responsible for our shifting, which C is responsible for our shifting right and left. But we do have to account for the fact that B is there. Okay. So a horizontal shift for our graph is going to be whatever C over B is. Now you might ask, like, how'd you get C over B? If you want to make a note somewhere in your notes about this, that C over B is coming from taking that Bx minus C and setting it equal to 0. That's what you do when you try to figure out, like, what's the horizontal shift for x minus 5 squared. Take x minus 5, you set it equal to 0, x was 5, so you shifted it 5 to the right. Okay. So if you solve this equation, you get bx equals c, and then that's where that c over b is coming from. Okay, so you have to take into account the horizontal stretch or shrink there. D is going to be most like k. So remember, k is that thing that's like added, subtracted on the front or the back of your function, so it can be like rearranged. You can have D out front, you can have D in the back. But that's just your vertical shift. It's not affected by B because it's a vertical shift. Okay, so it's just whatever D is. And D looks like the sign that it is. And so we're going to take those things. This is what I'm going to have you practice on your homework tonight, writing out the starting point for what we're going to call the frame of your graph. And so that's how we're going to graph tomorrow, so we call the framing method. So the starting point for your frame will be C over B. Sorry, C over B, comma D. Okay, so we are going to do some examples like what I want you to do on your homework assignment. Okay, so the first example that I've got is an equation, y equals 4 times sine of 6x. I want you to do these things for your homework. Identify your amplitude and periods. Make a note if the graph should be reflected, because we'll need that information for when we actually graph. And also identify the starting point. The book is going to ask you only to do amplitude and period, but I would like you to do those extra 2 things. I want to take one.
What kind of extra?
The starting point and the reflection, if it exists. Okay, so let's talk about amplitude. Y equals 4 times sine 6x. What number is, or what value is responsible for the amplitude there? 4, the thing being multiplied in front of sine or cosine is your amplitude. And we would do the absolute value of 4, which is 4. Is there a reflection that you should make note of? No, because 4 is not negative. Okay, so that's your A value. What about period? We would do 2 pi divided by 6, which we can then reduce to pi over 3. So we have done a horizontal shrink for our sine graph. Instead of taking 2 pi to repeat itself, it does it every pi over 3. So we're going to see a much more jagged graph that we graph. What are your values for C and D? Zeros, right? I mean, this is like A times sine of BX minus C plus D, and we've got nothing added or subtracted on the back. So when you do your starting point, your C over B would be 0 over 6, which is just 0, and your D value would be 0. So basically what it's saying is, there is a horizontal shrink caused by the B, but there's no horizontal shifting. There's also no vertical shifting. So we're still going to have the same start point that sine would normally have at 0, 0. Can you try this one for me really quickly? Y equals negative 2 cosine pi x. Okay, lean over to people around you. Tell them amplitude, period, starting point. Yeah.
But you also take there would be a reflection.
Amplitude is?
2.
2. What else are you going to tell me?
Period is 2.
Okay, the period is 2 pi over pi, which is 2.
Reflection.
Oh, there's a reflection. Okay, because of the negative. And starting point? 0, 0 again. Okay, so let's look at one that has a different starting point just really quickly before you leave me. Y equals 1 minus 3 times the sine of x plus pi. Y equals 1 minus 3 times the sine of x plus pi. Okay, amplitude is what? 3. What else are you going to tell me right when you look at that amplitude? There is a reflection because it has a negative in front. Remember, amplitude is the thing that's always getting multiplied in front of the sine or cosine. So we're looking at the 3 and not necessarily the 1 at the very front of the equation. For period, we would say 2 pi over 1, or just 2 pi. Okay. And then starting point, my C value, because it says plus pi, is really negative pi. So it'd be like negative pi over 1, because that's my B value, which would be negative pi. And what's my D?
Positive 1.
The positive 1 at the very front. Okay. So now we have a new starting point at negative pi, comma 1. Do those things on your homework, even though the book says only amplitude period. Thank you for staying in a couple extra seconds. I really appreciate it. Today is Wednesday, so go to advisory.